1.1, real numbers in the number line. Russell, that math man, back at it again. So we have finally reached calculus, except we're still not in calculus. This is just a review of things that we need to know from Algebra 2, a little bit of pre-calculus, a little bit of Algebra 1. And this is stuff from way, way back, for being honest. So, real numbers are numbers that can be expressed as decimals. They don't have to be a decimal, but they can be expressed as a decimal. If I have just the number 1, that would be 1.0. So it can express that as a decimal. It's just not that it's always going to be a decimal. Oh man, a little writing thing ain't working. I hate it here. I fixed it. Real numbers are numbers that can be expressed as decimals, such as 1.5, 1.66 repeating, 1 point. I just made that number up. That's not even, there's no point in even reading it. The whole point is they can be decimals, but they don't have to be. On the real number line, each number corresponds to exactly 1 point on the real number line. That creates a one-to-one correspondence. So I can't have, that's all this is saying. Don't let it confuse you. All this is saying is that if I'm at this point, that point is exactly 1.33. It's not 1.333 and 1.335. It's just this 1 point, 1.333. This back here would be like negative 9.5. It's not negative 9.5 and negative 9.6. That can't happen. It's only 1 point. It's only one number. That's all it means when it says one-to-one correspondence. Each number has exactly 1 point that it falls on, and that's it. The algebraic properties say that real numbers can be added, subtracted, multiplied, and divided, except by 0. You can add, subtract, multiply by 0, but you can't divide by 0. Remember Cookie Monster. To produce more real numbers under the usual rules of arithmetic. And again, you can never divide by 0. All this one is saying is that when I'm looking at inequalities, if A, B, and C are real numbers, so any number you can think of that's not imaginary, then if A is less than B, then A plus C is less than B plus C. That just makes sense to me. It should just make sense to you. A is our first number. We could call that 2. 2 is less than 3. So if I say this is 2, this is 3, and this is 4. So if 2 is less than 3, then 2 plus 4 is less than 3 plus 4. That's 6, that's 7, that's true. Imagine that. If we add the same number to both of our original numbers, then the first one's going to be less than the second, if the first one was less than the second to begin with. So this is some hard stuff. If A is less than B, then A minus C is less than B minus C. I think we can all agree that that's going to be true as well. If I subtract the same number from both sides, if the A was less than B, and I'm subtracting the same thing, it's still going to be less than B. Number 3, A is less than B, and C is greater than 0, then A times C is less than B times C. Kind of the same thing there. Number 4, if A is less than B and C is less than 0, then B times C is less than A times C. Why would that be true? The reason that would be true is because C would have to be a negative number. If I multiply 1 by a negative 2, so say that I'm changing my A, B, and C now so that the numbers are less than 0. So I'll say 1, 2, and this is -4. Then if I do b, which would be 2 times -4, that is going to be less than 1 times -4. 2 times -4 is -8, and 1 times -4 is -4. So yes, -8 is less than -4. Number 5, if a is greater than 0, then 1 over a is greater than 0. So if I have any number that's bigger than 0, if I divide 1 by that number, it's still going to be bigger than 0. Last one, if a and b are both positive and both negative, then a is less than b, and 1 over b is less than a. That one might seem a little trickier, but if I'm saying that this is 2 and this is 3, then 1/3 is less than 1/2. That is true. Like if I have $100 and I give you 1/3, I'm giving you 33.33, so $33.33. If I have $100 and I give you half, then I'm giving you $50. The completeness property of the real number system says there are enough real numbers to complete the real number line, in the sense that there are no holes or gaps in it. The reason that this is important is because many theorems from calculus would fail if the real number system was not complete. All this one is saying, wow, magically Desmos came up. I like that I can pause my videos and bring it up. All this is saying is that if I have numbers from 0 to 5, right, it looks like there's a gap between 0 and 5 because there's no other numbers listed. But if I just keep scrolling in, if I pick one random point, as I get closer and closer to that point, you see it just keeps filling in. There are numbers to fill in this point. Always. So even as I just keep getting smaller and smaller, it's 2.6021. This is 2.6022. Then in the middle would be 2.6021.5, because it's halfway between 602 and 6021 and 6022. So every actual number is getting filled in. That's all that this theorem is saying. That's all that this is telling you, is that no matter what, every actual number does exist. No matter how far I zoom in, there's a number that represents this point. It just keeps breaking down smaller and smaller. Now, I think we've taught this every year since Algebra 1. Natural numbers are a subset of the real numbers. They're also referred to as counting numbers. They're referred to as counting numbers simply because these are the numbers that we started to count with. Whenever you were learning to count as a little baby Glow, just sitting there counting, she didn't start with 0. You started with 1. So that's why they're referred to as counting numbers. Whole numbers is 0 together with the set of natural numbers. So we have the set of natural numbers, which is 1, 2, 3, 4, 5, going on forever. The whole numbers, we're just adding 0 to that. Decimals that end are called rational numbers. A real number that cannot be expressed as a ratio with an integer numerator and denominator is called an irrational number. Pi is an irrational number. Oh, the air horn sounds, lets us know that it's time for our word of the day. Our word of the day is irrational. Irrational is our word of the day. If you send me the word irrational within the next, let's call it 48 hours, I will give you 10 bonus points for your quiz. Your chapter test that you just took. So I will add 10 bonus points onto your chapter test score if you send me the word irrational in an email within the next 48 hours. Okay, back to the lesson. Decimals that end are rational numbers. So if I have a decimal like, say, 0.55, can I express that as a fraction? Yes, that's just 55 over 100. That is 0.55 as a fraction. I could reduce that, but the whole point is, as soon as I can make it into a fraction, I'm done. Pi is an irrational number, and the reason it's irrational is because it goes on forever. There is no stopping pi. Intervals. A subset of the real line is called an interval if it contains at least two numbers and contains all the real numbers lying between any two of its elements. For example, the set of all real numbers x such that x is greater than 6 is an interval because it starts with 6 and it's every number that's greater than that. So that's 6.1, 6.001. So that's at least two numbers, and it contains everything between 6 and infinity, going on forever. The set of all x such that 2 is less than x is less than 8 is also an interval. That's every number between 2 and 8. If we go back to geometry, man, I bet you guys had a great geometry teacher. Geometrically, intervals correspond to rays and line segments on the real line, along with the real line itself. Intervals of numbers corresponding to line segments are finite intervals. If you remember from back in geometry, when we talked about rays, there was an endpoint, and then it went on forever in one direction. Good band, One Direction. Well, now segments had endpoints on both ends. They came to a stop in both directions. So segments are finite intervals. That would be like, hang. That would be like 2 less than x less than 8. This would be a finite interval because it stops at 2 and it stops at 8. X greater than 6 is an array because it starts at 6. I should have an open circle here. Starts at 6 and continues on forever. Intervals corresponding to rays in the real line are infinite intervals. Oh, snap. A finite interval is said to be closed if it contains both of its endpoints. So basically, it would be closed if it's a greater than or equal to sign, or a less than or equal to sign. That makes it closed. I guess we should make this a closed interval on both levels. So 6 less than or equal to x, and say 4. Because here, if I'm looking at this segment, it includes the points 4 and 6, which are the endpoints. The equal sign underneath the less than shows that. So that would be a closed interval. An interval is half open if it contains one endpoint but not the other, and it's open if it contains neither endpoint. If I say x is greater than or equal to 6, that is half open because I'm going from 6 to infinity. I can't contain the endpoint infinity because it's not ending. It goes on forever. It's open if it contains neither endpoint, meaning that if I have x less than 6 and greater than 4, I'm not containing 4 or 6. It comes right up to it and stops. It's infinitely close. Okay, we will pick up there tomorrow.